Assalamualaikum and hello everyone. In this video, we will discuss past year question for the year of 2019-2020. We will discuss question 3 involving chapter 4 chemical bonding. Okay, question A, explain each of the following statement. So this question gives us 3 different statements, and these 3 questions will get you 10 marks. Okay, so first let's look for question number 1. Question 1 Roman, upon reaction with fluorine, oxygen forms only OF2, whereas sulfur forms SF2, SF4 and SF6 molecules. Okay, so first what we're going to do is actually I'm going to draw the Lewis structure for the following compound. So first thing first, before you draw the Lewis structure, you have to know or you have to write down the electronic configuration of the atom to know for each atom what is the valence electron. Once you have written down the electronic configuration, then you know what is the valence electron. Again, the valence electron is your highest n. So for the case of oxygen, the highest n is n equal to 2. So the number of valence here is 6. For sulfur, the highest n is n equal to 3. The valence electron is also 6. For fluorine, the highest n is n equal to 2. And the valence electron here is 7. Next is you have to draw the Lewis structure for OF2, SF2, SF4 and SF6. So this is the Lewis structure for all the molecules mentioned in the question. So I have my OF2, SF2, SF4 and SF6. So here what we have to do is actually we have to explain why. Okay, again the difference is that between oxygen and sulfur. So I'm just going to look based on the central atom. So oxygen here, I have how many electrons? Here I got 2, 4, 6, 8. Here I got 8. Okay, the sulfur here is 8 as well. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this sulfur for SF4. So when we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sulfur here got 10 electron. Well, for this sulfur got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12. This is the number of electron involving our central atom. As you can see, oxygen can already contain 8, which is the maximum octet lah. Okay, but then for the case of sulfur, we have 8, 10 and 12. Here I have more than 8. So this is what we call our expanded octet. Expanded ni means that it is more than 8. So we have to explain lah. Okay, why the oxygen can only hold 8 electron while the sulfur can hold more than 8. Okay, so first what I would like to mention is about the difference is that the electronic configuration lah. Okay, so here when you can see oxygen, the highest n is n equal to 2, sulfur is n equal to 3. So back to our chapter 3, periodic table, where's the position? So if the highest n is n equal to 2, so it means that our oxygen is in period 2. Whereas sulfur is in period 3. So that is my first point. So what is the difference? Okay. Then remember the oxygen here holds 8 electron. Here is 8. For sulfur here 10. For sulfur here is 12. So now I've mentioned that the sulfur has more than 8 electron, which is considered as our expanded octet. Okay, so why sulfur can form expanded octet is back to the period or to the n lah. Okay, so for the oxygen, the n is n equal to 2. Okay, so for n equal to 2, L could only be L equal to 0 or L could be equal to 1. So it means that for n equal to 2, we only have 2s and 2p. But for the case of sulfur, n is n equal to 3. So when n equal to 3, our L could be 0, 1, 2. So when n is equal to 3, our possibility is that we can have 3s, 3p, and 3d. Okay, so when n is equal to 3, we can have 3d orbital. But when n is equal to 2, we do not have any 2d orbital lah. Okay, so what does it mean when we have empty d orbital? So that's why our sulfur can have more than 8 because here we have empty 3d orbital. Because as you can see in the electronic configuration itself, 3s2, 3p4, maksudnya 3d is not being used, tapi it is there. We can use the empty 3D orbital. For the case of oxygen, there's no 2D or there's no D orbital itself. Okay. So we have to mention that the sulfur can use the empty d orbital, while oxygen, there's no empty. And remember, when L equal to 2, L could only be equal to 0 and 1, which means that 2s2p lah. For the case of oxygen, highest n is n equal to 2, there's no 2d orbital. So that's what I've mentioned here. O has no d orbital, as we have our empty d orbital, which can be used to fill the electron. Okay, that's why it can form expanded octet. That's for question 1 Roman. Question 2 Roman. The shape of PF3 molecule differs from that of an IF5 molecule. So just please correct this one. It's supposed to be PF5 molecule. Okay, so this is again about shape. So what's about shape? We have to know the molecular geometry lah. So how to know the molecular geometry? First, we have to draw the Lewis structure. Okay, so how to draw the Lewis structure? First thing first, what we need to do is we have to write down the electronic configuration for the atom to determine what is the valence electron. The proton number for phosphorus is 15, so electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Fluorine is 9, 1s2, 2s2, 2p5. But this is iodine. Iodine is quite a long one, it's 53. So it's either you want to remember that iodine is halogen, group 17, so it means that it has 7 valence. Or if you write down the electronic configuration, it will be this one lah. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So here you got your value to be 20. Okay, and then 3d10, 30 here. Okay, and then for 4p6, you get 36. 5s2, 38. 3d10, you get 48. And last but not least, when you add the 5, you will get 53. Again, iodine, the proton number is 53. Okay, so why do we have to write down the electronic configuration? This is to determine the valence electron, so that later on we can count the total. Okay, so for phosphorus, again, we consider the highest n to determine the number of valence. So phosphorus, the highest n is n equal to 3, so the valence here is 5. For fluorine, the highest n is n equal to 2. So when we add up here, you got 7 valence electron. So for iodine, okay, again, highest n is n equal to 5. This one. Okay, and then the valence electron, 5s2, 5p5. So total is 7. So that is the valence electron for each of the atom. Now we have determined the valence electron. We can calculate lah the total valence electron itself. Okay. Now we start with our PF5 molecule. So again, phosphorus, we get 5 electron. Fluorine, there is 7 valence electron, but there's 5 of it, so 35. Total, you will get 40. Okay, and then determine the center. The center is this number of atom lah in the molecule. In this case, our phosphorus will be the center. It is connected to 5 fluorine. 1, 2, 3, 4, 5. Then remember, for each one bond, we have 2 electron. Since we have 5 bond here, so we will minus 10. So now we are left with 30 electron. Okay, then we make sure that the octet already achieve octet. Hydrogen sahaja will achieve duplet, 2 electron. Another atom, another terminal must be 8. So right now, our fluorine, for example, this fluorine already got 2. So it needs 6 more. Okay, not only this fluorine, all the other 4 fluorine pun must achieve octet. Okay, so 30 electron are used, so then we are left with 0 electron. So this is the Lewis structure. So for the Lewis structure, does not follow the shape lah. It's fine. So right now, what we're going to draw is actually the shape. So the shape or the molecular geometry. So to determine the shape or the molecular geometry, first you have to write down the class. So what does it mean by class? Generally, class is A, B, X, E, Y. B stands for bonding pair. How many atom is it bonded to? E stands for lone pair. How many lone pair at the central? A ni our central lah. Okay, so in this case, our phosphorus bonded to 1, 2, 3, 4, 5. 5 fluorine. But then it does not have any lone pair, so the class will be AB5. You have to explain what does it mean by this AB5. We mentioned that this is 5 bonding pair. After you have determined the class, you have to determine the electron pair geometry, or you can denote it as EPG. So how to determine the electron pair geometry? You add up your bonding pair plus lone pair. In this case, lone pair 0, bonding pair is 5. So we have 5. So what's the shape for 5? Okay, this one you have to memorize lah. So here is the simulation. The link is in the description itself. So when you click the link, so write down, click the model. Okay, and then based on this structure, we have 2 bonding pair. But we want for our question just now, PF5. So 1, 2, 3, 4, 5. Okay, and then check the bottom left here. We have our electron geometry. So electron geometry, the name is trigonal bipyramidal. Okay, so electron geometry and molecular geometry is two different things lah. So when you click this one, the molecular geometry is the same. Why? Because there is no lone pair on the central atom. Based on the simulation, again, since our central atom has no lone pair, the electron pair geometry and the molecular geometry will be the same lah. Okay, so now then you have to draw the shape based on the molecular geometry itself. So 5 trigonal bipyramidal, there are 2 ways to draw it. Yang ini pun sebenarnya diterima lah. Macam mana kita nak draw kalau ada 5? Remember dia ada kepala, ada tangan, ada kaki. So it's 5. Or if you don't want to draw it this way, you can also draw it in terms of this one. We have our central, we have atas, bawah, lepas tu belah kiri kita, lepas tu kanan ni kaki dia macam kangkang. Okay, and then make sure it is bonded to the fluorine and show that each of the fluorine tu already achieve octet. Okay, so there's another way for you to draw lah. Both is accepted. Is it actually the same? So why did I say that it is the same? If I rotate it this way, nanti dapat jadi macam ni jugalah. So you can draw it any way that you want lah. This shape or this shape. It's actually the same shape lah, tapi cara dia lukis dia lain sikit. Okay, so that is for PF5. So that's the first part of the question, the shape of PF5. Next, we have to do the IF5. So again, for the calculation, I has 7 valence electron. Okay, and then fluorine also got 7, but then we have 5 of our fluorine, so it means that we have 35. So the total electron is 42. So which one is the center? The center is the least number of atom in the molecule. So I is our center, bonded to 5 of our fluorine. And then minus 10 electron. Remember that each bond have 2 electrons. So we are left with 32. So where do we put the 32? Make sure that each of the octet achieve each of the terminal atom achieve octet. Fluorine only got 2 electrons. So it needs 6 more. Okay, for each of the fluorine will have 8 electrons. Minus for each of the atom 6 electron. There's 5. So what we have left is 2 electron. So where do we put our 2 electron? We put the 2 electron on the central itself. Okay, so minus 2. Okay, then we are left with 0. Okay, this is the Lewis structure. Next, what we have to do is we have to determine the class. So class is A, B, X, E, Y, B bonding pair, E lone pair. So A is for our central atom lah. So bonding pair we have 1, 2, 3, 4, 5. Lone pair we got 1. So A, B, E1 ataupun A, B, E pun it's fine. Don't forget to explain what does it mean by B5 and E1 ni. It means that we have 5 bonding pair, 1 lone pair. Next is the electron pair geometry. So how do we know the electron pair geometry? Add up bonding pair plus lone pair. In this case, electron pair geometry is 6. So what is 6? It's not the same as previous one. This one is for 5. This one is for 6. Okay, so back to the simulation. So if we have 6, okay, so again, if we have 6, in this case, I'm just going to draw the 6 bonding pair. As we can see, the electron geometry is octahedral. How about the molecular geometry? Previous one, we can see the electron pair geometry is the same as molecular geometry. This one, if the center has no lone pair. But this case, our center has lone pair. So these two will be different lah. Okay, so how do I know the shape? So actually here, you draw the electron pair geometry first. So iodine, we have actually, it's supposed to have 6 lah kan? Total these two. Okay, so for the 6, 1, 2, 3, 4, 5, 6. Okay, but then again, when we based on the class itself, we can see there's 5 bonding pair. So it means that I want only 5 bond. So now we have 6. So which one I'm gonna remove? Up to you lah. Nak cabut yang kepala ke nak cabut yang kaki dia? Senang cabut kaki lah. Okay, then once you remove the bonding pair, you substitute it with the lone pair. Okay, so then what's the rest? This one, don't forget to write down your F as well as the lone pair itself. Okay, so what's the name of this shape? This one you have to memorize. Okay, actually this here is actually a square. So, but then it will form a pyramid. So the name is square pyramidal. So for our IF5, we have 5 bonding pair, 1 lone pair. So I'm going to remove one of my bonding pair. I'm going to add 1 lone pair. So when you click the bottom left, the molecule geometry, you can see it is square pyramidal. Okay, so how can I see it is square pyramidal? Okay, actually, as we can see the X there, that is your square. Okay, the one ball molecule towards us to show that it will form a pyramid lah sebenarnya. Okay, so that is the shape for IF5. The electron geometry and the molecular geometry will be different since there is our lone pair. So that's for question 2. Remember, for the Lewis structure, it's fine if you don't follow the shape. Once you have written down your class, your electron pair geometry, your molecular geometry, then you have to draw the molecule based on the shape itself lah. Shape ni sama jugalah dengan molecular geometry. Okay, so that's the solution for question 2 Roman. Question 3 Roman, of the 3 possible resonance structure for OCN minus below, number 3 is the best structure. So here we have 3 possibility structure for OCN minus. Okay, so it is determined that OCN minus is the best. So how do we determine this is the best structure? So this one we have to calculate the formal charge. Formal charge of each of the atom in the molecule itself. Okay, so how do we calculate the formal charge? Formal charge is the number of valence electron minus number of bond minus non-bonding electron. Okay, again, how do we calculate non-bonding electron? So for example, if I have my HCl here, okay, here my non-bonding electron for the case for HCl is 6. 1, 2, 3, 4, 5, 6. Non-bonding electron is not the same as lone pair. Okay, non-bonding electron, calculate how many electron lah. So for example, for the chlorine we have 3 lone pair. But how many non-bonding electron? Non-bonding electron is 6. Okay, so why do we have to calculate the formal charge? Because once we have calculated the formal charge, we can choose the most possible by using these 3 reasons. First one, the atom must have the lowest formal charge. Usually, we want each of the individual atom to get 0 lah. Or the negative value of the formal charge must be located on more electronegative atom, or positive formal charge located on the least electronegative atom. For this question, it has given us which one is the best one. It's this one. Okay, but then we have to mention which one is the reason that we're gonna use for stating that this is the best structure. Okay, so what I'm going to do now is actually we're going to calculate all the formal charge for each of the atom in these 3 structures. So I have redrawn this structure again based on the structure given in the question. Okay, but then we can't see any of the non-bonding electron in the atom itself. So what we need to do is check whether each of the atom already achieve octet or not. So for example, this oxygen only got 1, 2, 3, 4. So to achieve octet, it needs 4 more electrons. For the carbon itself, this carbon got 1, 2, 3, 4, 5, 6, 7, 8. So the carbon already achieved octet. There's no need for the lone pair. Okay, so nitrogen here already got 1, 2, 3, 4. So it needs 4 more to achieve octet. That is only for structure 1. Then you have to check for the structure 2 and structure 3. So this is the Lewis structure for all the molecule with complete octet lah. Okay, just make sure. Again, when you check here, our oxygen already got 1, 2, 3, 4. So where's another 4? That's why we have to put the electron. Again, all of this will achieve octet. Only Berbal will have incomplete octet lah. So this one nitrogen tak boleh lah. Kat sini dia baru 2 kan. So again, Berbal incomplete. Other atom must achieve octet. Okay, now we proceed to the calculation of the formal charge. Okay, so formal charge is equal to number of valence electron minus number of bond minus non-bonding electron. Okay, so how do I determine the number of valence electron? For this one, you have to refer back to your list of constant to determine the number of proton. Then you can write down the electronic configuration to determine the valence electron. So this is the electronic configuration for each of the atom, and then we can see here that the oxygen, the valence electron is 6, carbon is 4, nitrogen is 5. Again, how do we know the valence? Calculate the highest n. For this case, all the n is n equal to 2. This one 6, for carbon 4, nitrogen 5. Okay. Then now we can proceed with the calculation. So I'm just going to show, okay, for the structure 1. We will start with oxygen. Oxygen, we have valence electron is 6, number of bond is 2, non-bonding electron is 4. Again, 2 because this 1, 2, 4 because of 1, 2, 3, 4. Carbon, the valence electron is 4, minus 4 minus 0 equal to 0. Again, minus 4, why? Because 1, 2, 3, 4. Minus 0 because we have no non-bonding electron here. Next is nitrogen. Nitrogen have 5 valence. Minus 2 minus 4 is equal to negative 1. Okay, so why minus 2? 2, we have 2 here. 4 because we have 4 non-bonding electron. Okay, so I've showed you the calculation step only for structure 1. Then you can attempt for structure 2 and 3 by yourself. So these are all the formal charge of each of the atom in these 3 structures. Again, for this case, it mentioned that the structure 3 is the best structure. Okay, but then when you look back, based on the most plausible, the lowest formal charge, we can't use this. Okay, lowest formal charge means that each of the atom have the lowest value lah. Okay, it's not because when we add up all these value, we will get negative 1, negative 1, negative 1. Why do we get negative 1? Because the overall charge memang negative 1 lah. Sini negative 1 kan? Okay. If we use the lowest formal charge, it is the same as structure 1. Structure 1 dengan 3, dua-dua ni lowest formal charge because we got 2, 0 and 1 of negative 1. Okay, so we can't use this one. Okay, so what is the difference between 1 and 3? So number 2 ni memang tidak lah kan? It has negative 2, so bukan lowest formal charge. Okay, so the difference between structure 1 and structure 3 is that the negative 1 for structure 3 is on oxygen, whereas for structure 1, the negative is on nitrogen. Okay, so go back to the most possible. Negative formal charge must be located on the more electronegative atom. So what is electronegative? Okay. So please add in your notes the trend for electronegativity. So it will be increasing across the period and it will actually decrease down the group lah. So that's why this arrow I put it towards the fluorine, it will be increasing. Okay, what is electronegativity? Electronegativity ni means ability to attract electron lah. Okay, so usually when we're talking about group 17, this is considered high electronegative. Okay, why? Because for group 17, it only needs 1 more electron to achieve octet. So that's why usually we mention group 17 high electronegativity. But for this case, for the example here is between nitrogen and oxygen. It's not group 17, there is actually period 2 element. For period 2 element, the order of increasing electronegativity is SK0. SK0 stands for carbon, nitrogen, oxygen, fluorine. So right now we have nitrogen and oxygen. So between these two, oxygen is more electronegative. Okay, so in this case, we want the negative formal charge more on the electronegative, which in this case is oxygen. So case of structure 3, the negatively charged is on oxygen. So that's why structure 3 is the best structure. Okay, so how do we write it down in sentences? So we write down that the structure 3 is the most plausible or the most possible because negative formal charge appears on more electronegative atom. Okay, so if the question asks you to determine the most possible, the most plausible, then you have to calculate the formal charge. This question, they didn't calculate it, but then they did tell us that this is the best structure. So how do we rationalize it? Then we have to calculate the formal charge, and we mention the reason itself. Okay, so that is the solution for question 3 common. For question B, illustrate the hybridization of the central atom in SF4 using orbital diagrams. Show and label the overlapping of orbitals in the molecules. Okay, so before you illustrate the hybridization, okay, so what first thing that you need to do is actually you have to determine the molecular geometry lah. So how you determine the molecular geometry? Back to your Lewis structure. So to draw the Lewis structure, first what you need to do is actually refer back to your list of constant to determine number of proton for the S and F to determine what's the valence electron. So once you have written down the electronic configuration, you can see that the sulfur has 6 valence electron while the fluorine has 7. Okay, why? Because again, for the valence electron, refer to your highest end. For sulfur, we got 6. For fluorine, we got 7. Then now we may proceed with the calculation of the total valence electron. Sulfur, we got 6. Fluorine is 7, but we have 4 of our fluorine. So 4 times 7, 28. The total is 34. Next is check to check which one is the central atom. The central atom again is the least number of atoms in the molecule. In this case is sulfur. So this sulfur will be connected to 4 of our fluorine. Each one bond here that connected the atom contains 2 electrons. Right now we have 4 bond. So 4 bond means that we have to minus by 8. So we get 26. Next is to check that for each terminal atom to achieve octet. So for the fluorine, now it only got 2 electron. 1, 2. So it needs 6 more electron to achieve octet. Okay. So not only for this fluorine, for all these 4 fluorine, we'll need 6 more electron. Electron used is 24. So what we have left is 2 electron. So where should we put the remaining electron? Since the terminal already achieved octet, we're going to put on our central. So minus 2. So this is our Lewis structure. Okay, then next we may proceed with the class to determine the molecular geometry. So for the class of SF4, it will be A, B, 4E. So up to you, E1 boleh, E pun boleh. Okay, so what does it mean by AB4E? AB4E stands for 4 bonding pair and 1 lone pair. Okay, so this is the class. Then you have to determine what is the electron pair geometry, EPG. Electron pair geometry is when you add up your bonding pair plus lone pair. So total here, 4 plus 1 is 5. So 5, so what is the shape of 5? If you refer to the simulation, we know if 5, right now we only have 2. So 3, 4, 5. Okay, please refer to the bottom left. The electron geometry here is trigonal bipyramidal. Okay, next for the molecular geometry or your shape, since our central atom has lone pair, so the electron pair geometry will not be equal to molecular geometry lah, will be different. So how do we know the molecular geometry? So actually the hint is you have to draw based on the electron pair geometry first. So for me personally, what I would like to draw is, okay, we have our central, ada kepala, ada tangan, ada kaki. Okay, and then but right now we have, this is 5 bonding pair. This one needs 4 bonding pair, 1 lone pair. it means that kita akan cabut or we're gonna remove one of the bonding pair and substitute it with our lone pair. So kita nak cabut mana? Cabut kepala. So letaklah sini kita punya lone pair. So the rest of it, the rest of bond, we're gonna connect it with our fluorine. Okay, so what is the molecular geometry? Okay, so what's the name for it? The name is seesaw. Again, we can refer back to our simulation. So this one is we have 5 bonding pair. But then SF4 is 4 bonding pair. So I'm going to remove 1 bonding pair. I'm going to add 1 lone pair. Okay, so the electron geometry is still trigonal bipyramidal if you look at your bottom left. But then the molecular geometry, the name will be seesaw. Okay, so this one will be our seesaw lah. So this is the way that I've drawn it. If you draw your trigonal bipyramidal as this one, so it means that we're going to remove this one lah. This will be our lone pair. It will become like this. F, F, F. This will be our seesaw. Okay, both is accepted. Okay, so right now we have known the shape. Okay, then we can determine what is the hybridization. For the hybridization, it actually depends on the total electron pair or when you add up bonding pair plus lone pair. Okay, so hybridization we have from sp until sp3d2. Okay, again, why we don't have any sp4? Because p only has 3 orientation lah. So that's why sp3. Okay, so then when you add up, okay, how to remember this one again? SP means that we add S1S plus 1P, we got 2. SP2 means that we add 1S plus 2P, total is 3. Why do we get SP3D2? 1 plus 3 plus 2, then we got 6 here lah. Okay, for this case, what we have here, again, that's why we have to draw the Lewis structure and then determine the class. You know that the total will be 5. So 5 will be sp3d. So then we know that our S is sp3d hybridization. Next, after we have determined the hybridization of the central atom, before we go to the hybridized step using the orbital diagram, that ground state, excited state, hybridized state, what I would like to label is that from the structure, I like to label how many pi bond is there, how many sigma bond is there, and how many lone pair present. Okay, so for this case of SF4, what we have is we have 1, 2, 3, 4. We have 4 sigma bond. So what does it mean by 4 sigma bond? It means that for the hybridized state, then we will have 4 sigma bond, 4 unpaired electron. Okay, so what does it mean by the lone pair? Lone pair means that we will have 1 paired electron, which will be hybridized. Okay, in this case, we don't have any pi bond. So what is the example if we have pi bond? So for example, if you have oxygen, then the first bond is sigma, second bond is pi. Okay, nitrogen, triple bond. Again, first bond is sigma, second bond, pi, the third bond is pi. In the case of SF4, there's no double or triple bond lah. So we only have 4 sigma bond. So I'm just going to label that 4 sigma bond, 1 lone pair. What does it mean? So again, in this case, 4 sigma bond means that we need 4 unpaired electron for the hybridized orbital, and 1 lone pair means that we will have 1 paired electron in the hybridized orbital. Again, the hybridized must be sp3d hybridized. Okay, then now we may start with our ground state, excited state, hybridized state. Okay, so first again, we must refer back to the electronic configuration. Okay, for the ground state, okay, sulfur, we know that this is the electronic configuration and it has 6 valence electron. Okay, usually for the hybridization step or the hybridization process, we're only concerning ourselves with the valence lah. In this case, n equal to 3. So our 3s2, 3p4. Okay, so what we have now is actually we have 2 paired electron and 2 unpaired electron. Okay, but then when we back to the list, we can see that we need 4 unpaired and 1 paired electron. So only this one, we need it to be in pairing. This one must be a single lah. Then if this one single, then we will get our 4 unpaired electron. So how do we make it single? How do we excite it? Okay, sebenarnya hint on the hybridization. Since the hybridization itself, we see that is sp3d, means that we're going to use our, in this case, we're going to use our 3d orbital. Okay, Again, why 3D orbital we have 5? Because when 3D is L equal to 2, M equal to -2, -1, 0, 1, 2. So there must be 5 platform here lah for 3D. Even though it is not used, you're just gonna leave it there lah. Okay, we're gonna use it for the excited state. Okay, again, for the paired electron, we only want one lah. Yang ni ha. So it means that this one we have to excite into one of our d orbital. That's why the name is sp3d. So the excited state must again follow based on this one lah. Means that we excite one of the paired electron to the d orbital. That's why later we get sp3d. Okay, last but not least must be the hybridized state of sulfur. Okay, again for the hybridized state, we have sp3d, means that we have 5 lah. 1, 2, 3, 4, 5 platform here. Okay, and for the sp3d, we need 4 unpair. 1, 2, 3, 4. And then we need 1 paired electron, the first one. So that is for the hybridized state of S. This 3D orbital is not being used, so we're just going to leave it there lah. Just going to label it as 3D. So that is for the central. Next, you have to show for the terminal as well lah, which is our fluorine. Fluorine S1, S2, 2S2, 2P5. Again, for the orbital diagram, only for the valence electrons. This will be the orbital diagram for the fluorine. Terminal atom only for the ground state. Okay, for the terminal atom. Then now we may proceed with the shape or the orbital overlapping. Okay, so again, orbital overlapping must follow this one, SF4 ni. Okay, again, SF4, the shape is seesaw, but originally it is based on trigonal bipyramidal. So how do we draw trigonal bipyramidal? Ada kepala, ada tangan, ada kaki. Make sure label all of it to be sp3d. Okay, and then for this case, we have 1 pair electron. 1 pair electron ni yang atas kali ni lah, yang dekat kepala. Tadi kita cabut kepala tu. Okay, so for the drawing here is my sulfur. Again, make sure label each of the orbital is sp3d. And here I have 4 unpaired electron. 1, 2, 3, 4. And paired electron is where is my lone pair is lah, at the top here. So next is actually we have to draw the F. F is 2p orbital. So I'm going to draw. Again, F we have only 4. And then where should I draw the 4 2p orbital based on the drawing of the shape itself. Okay, here I have drawn all my 2p orbital for fluorine. Okay, make sure you have drawn again, all of it will be paired up, so it will be opposite spin. Okay, and then don't forget to put, there's the sigma bond. Okay, for here 1, 2, 3, 4. Remember, each of it will be 2p, as well as label the fluorine atom itself. Okay, so the question is quite a long one because they ask you for the hybridization process as well as the overlapping. Question C, explain the difference in melting point between element in group 1 and group 17. So if the question asks about the difference in melting point, or sometimes it mentioned in boiling point, then we have to mention about the intermolecular force between the atom lah. Okay, but then for this case, it just mentioned generally in group 1 and group 17. Okay, because for the chemical bonding, not only we've learned about the hybridization, the shape, we also learn about the bond between the atom itself lah. Okay, so first what I'm going to do is actually I'm going to mention about the force that exists in group 1. So for the element in group 1, it actually between the atoms we have metallic bond. So what is actually metallic bond? Metallic bond is the electrostatic force of attraction between our positively charged cation as well as the sea of electron. Since here we have our negatively charged present, so there are a strong attraction lah, strong force of attraction between the cation as well as the negatively charged electron. So consider that this metallic bond is a strong one lah. Whereas for the element in group 17, it only have van der Waals forces lah between the molecule itself. Okay, for example, group 17 is halogen. Halogen, we have our fluorine, our bromine, our chlorine, our iodine, and etc. lah. Okay, so why we mention about this only have van der Waals forces? For example, here I have my F2. So F2 here, it is actually a non-polar bond. So how do I know that it is non-polar? Okay, kalau polar bond, it means that it have different electronegativity. Means that different atom. For example, if I have my CO. CO ni we consider polar bond. Tapi fluorine non-polar because it consists of two similar atom lah, same atom. So when it is non-polar bond, there is non-polar molecule. Polar ni means we have our pole. We have pole positive, pole negative. So this case, we non-polar, there's no positive or negative end lah. Okay, why this positive negative end is important? Because when we're talking about force of attraction, we mentioned about the opposite attract, we have the positive negative. But for the case of group 17, there's no attraction there. It's not there's none, it's just that it is weaker lah. Okay, which is because it only have van der Waals forces. Okay, so that is actually for each of the element or each of the group, that is the force of attraction. Next, we have to compare between these two. Now we can mention that the metallic bond is stronger than the van der Waals force. Again, metallic bond, there's actually attraction between the positive cation and the sea of electron. Okay, whereas the non-polar bond has none of it lah. Okay, and more energy is needed to overcome metallic bond because the force of attraction is higher. So what does it mean is that the melting point of group 1 is higher than group 17. Okay, so for this one, you have to explain based on the force of attraction present. Okay, so that is the solution for PSPM for the year of 2019-2020.